going to take like 32B because probably you didn't refresh your browser, Madav. This is for today. Like 30 to 31 is for today. So I did set this up. So all right. Any other problems beside 23 and 28? Raise your hand. That's it. Only these two. All right. All right. So,
sir, can you also do 24?
24. Okay. So 24. Okay. Anything else? Okay. So let's start with 23A. So let me share the screen here. Some people not yet here. All right, so 23A. A primary voltage, okay. What is the turn ratio, the primary to the secondary? So what else do we have here? We have 12 volts. You just count the whoops. You just count number of loops. That's it. I know it's all right. So you just look at Madav. So you just look. So number 23A. So the number of loops on the secondary coil is like 1, 2, 3, 4, 5, 6, 7. Right? Or if you don't want to count like the one on the top, that's fine. I mean, I don't really care here. And then for the primary, you just have 1, 2, 3, 4. That's it. So the turn ratio is just the number of turns in secondary over the number of turns in primary. So it's going to be like 7/4. Are you okay, Madav?
I was just wondering, like, how exactly you count the loops, because I kept on getting 6 instead of 7.
Well, I don't know. I'm as I said, I'm counting like the one like that starts on the top. 1, 2, 3, 4. Well, 1, 2, 3, 4, 5, 6, 7. Yeah, if you put 6, I mean, I really don't care. All right, so don't fret too much about this. I mean, you don't have like a transformer with such a few numbers of windings. Okay, so it's on the order of 50, hundreds, and 200s. So, whether you count 200 and 201, it doesn't really matter. All right, so 24. So let's do 24 here. A neon lamp requires a secondary output voltage of 1,000 volts. All right, so 1,000 volts at a resistance of 300 ohm. Transformer will run from a standard 120 volts outlet. So this is your primary here, right? What's the power consumption of the lamp's transformer? All right, so so the power is, of course, like I times V. It doesn't matter if you take like the primary and the secondary side. So if you put like if you take the secondary side here, you need to find like the current in the secondary coil, and you can find this like using those two values here. So if the neon lamp, so that's the load here, if the neon lamp gets a voltage of 1,000 volts and the resistance is 300 ohms, then you can use Ohm's law to find the current that goes through the lamps. All right, so it'll be like just this over this, and it'll be like 1,000 volts over the resistance, so 300, and I'll give you like 10 over 3 amps. Okay, and then you put this here, so 10 over 3 amps times 1,000 volts, and then you get this. Is that okay? So that's going to be the power here. Okay, are you good, Max? Can you do the other one, or you'll be okay?
Oh yeah. I just mixed up which one was primary and secondary.
Yeah, I told you the load is always on the secondary side,
Okay.
and the primary is always on the EMF source side.
Okay.
28C. So 28C. A step-up transformer has 500 turns on the primary side. All right. And 15,000 on the secondary side. Okay. The potential difference in that. Okay, so you're good. What is the power dissipated in transformer? So you just use like either IP times VP or IS times VS. Okay, so you can use like any of these two, Madav. All right. So and then you should be okay. If you take like B, they give you like the current in the secondary side, which is like 3 amps, and yeah, and they give you an A, they give you the potential in the secondary side. All right. So if you put these two right here, you're gonna find the power here, right? So this will be like 90 to 108. Wow, is it? No, there's one more zero. There you go. So that'll be the, so 100 and about like 10.8 kilowatt. Okay, Madav?
Yeah.
Yeah.
Is it always the case that on both the primary and the secondary side, it's just the same power
Well,
dissipation?
you always presume that like the transformer is 100% efficient. I mean, it's not true. Like no transformer 100% efficient, but you just assume this. Yeah.
Okay,
By
thank you.
conservation of energy, the energy in must be equal energy out. Yeah. Okay. So any other? All right. Good. All right. So let's continue here. There we go. So let's go back to that. All right, so I promised you here that we would sort of look at in greater details. It's coming, a little bit laggy here. We're going to look in greater details for this here transformer and how the current, it's coming, how the current is related in the secondary, in the primary, and the secondary current, secondary coil. So we know here that one is just like the derivative of the other, right? And then, and for that purpose, I'm going to look at this. It's coming. I'm going to look at this definition here. So we look at this one when we did our problems. That now we're going to look at that one here. So the magnetic field of an induced current always opposes the change in magnetic field that is causing the induced current. All right. So let's look at this. Okay. So I'll try to do my best here. All right. If you don't want to write this down, that's fine, as long as you understand like what I'm doing. Okay, so we're going to start with a magnet. There you go. There you go. And let's pretend here this is north, and let's pretend this is south. All right. Then you're going to have your magnetic field lines. Now I'm going to extend this, okay? It's for a purpose, all right? So I'm going to extend this like very much so, all right? I know there's, oops, comes back on the other side. All right. Outside of magnet, of course, always goes from north to south. And inside a magnet, always go from south to north. Magnetic field lines are never, they're always continuous, always continuous. Okay. So what we're going to do here is we're going to look at a point. So let's see here. We're going to look at this point right here. Like this point. At this point, the magnetic field is in this direction. Right? So we're going to call this like the initial magnetic field intensity right there. Okay. Now what we're going to do is I'm going to move this magnet closer. Well, closer to what? Closer. There'll be a coil here on the other side. Okay, so I'll draw a coil in a second, but let's move it towards the right. Okay. So in blue, I'm gonna sort of show like what this looks like. All right, so this is your magnet here that is a little closer, and then I'm gonna sort of show the magnetic field. All right. And of course, there's other ones here, right? Okay, the point I want you to understand here is this. As I move the magnet a little bit closer, this point here in space has seen a variation in magnitude, right, and in direction of the magnetic field. Okay, for pedagogical reason, I'm going to sort of pretend here that the direction here is in the same as this one here, just to make it like easier. And remember, if you get closer to a magnet, the magnetic field intensity will be bigger. So I'm going to make something a little bit bigger. All right. So of course, it's a little bit like it's a change in direction too, right? But just for, okay. So by moving this magnet, what happened here is at this point here, the magnetic field has changed in magnitude and in direction. But here I'm showing only in magnitude. So there has been an increase in magnetic field. All right, so that's the increase here, right? So at this point, at this exact point, the magnetic field intensity has gone up. Now, if we go back to this, let's look at this definition here. The magnetic field of an induced current always opposes the changed magnetic field that is causing the induced current. So let's go back to this. What happened here is this. I had like at this point here, the magnetic field intensity has gone up. There is a coil, which now I'm gonna write. So there's a coil right here. Okay. There's a coil right here. Well, let me sort of make it like a little bit like higher up here. Sorry. Let me make it a bit more right here. There's a little coil here. Okay. So what happened here is this. There'll be an induced current because as I move the magnet, there's a change in magnetic field and at any point in space. So at any point in space, there'll be an electrical field being generated. If there are wires around, it will sort of set a current into motion. Now, the second part here, if I go back to this, it says here. So once again, so let's go back here. So the magnetic field of an induced current always opposes the change magnetic field that is causing the induced current. So we come back to this here. At this exact point here, like the magnetic field has increased. This coil here, the induced current will be in such a way as to offset this increase in magnetic field. Well, if it wants to offset, sorry, if you want to offset the increase in magnetic field, what should it do? It should produce a magnetic field that is going towards the left to offset, to counterbalance the increase in magnetic field that has occurred. So if I wanted to do this here, so this coil here has to output, I should have put it like a little bit like more, anyway, that's not, okay. So the magnetic field yeah, it's not a very good. I think I'll have to move the coil again. Sorry, guys. Okay, so this is the induced magnetic field here. And what happened here is that at this exact point here, this exact point, the induced magnetic field will offset. I know the direction a little bit like different here, but it's not the key point here is that the induced magnetic field here produced by this coil will offset the increase in magnetic field has occurred here. All right. So these two here, all right. So this induced magnetic field cancels the increase in magnetic field. Magnetic field from the moving magnet. All right. So this induced magnetic cancel the increase. So this is all right. Now, if the magnetic field has to go this way, well, then we know what side this is. So this side has to be north. All right, it has to be north. So let me sort of put this a little bit like bigger here. Yeah. All right. So we know here that this has to be north. Well, if this is north, we use like Rydon rule number 2, then the induced current will be this way, right? All right, so you get the same answer as if you were using what you learned before, right? So the direction of the induced current, direction of the induced current is in such a way as to sort of bring what has caused the induction in the first place to a stop, right? So if you move your magnet towards the coil will want to stop this this magnet. And since I'm bringing the north side towards, in order to resist my moving it to the right, the coil has to output a north pole there, right? To have a force of repulsion. This is what you did in the first when you find out the direction of the induced current. Now, this is another way of looking at the problem here, right? So the induced current will be in such a way as to create a magnetic field called the induced magnetic field in such a way as to compensate for whatever change in magnetic field has been brought about because I move the magnet, okay? So I move the magnet towards it. I increase the magnitude. In magnetic field intensity. At this point, the coil will react in such a way as to offset this change in magnetic field to bring it back to what it was before. Okay. All right. So this is another way of looking at Lenz's law.
Wait, sir, is this always the case when you have a coil and a magnet?
What do you mean if it's always the case?
Like, so as you take the magnet and you move it towards the coil, so there will always be that like.
Yeah, yeah, it
Okay.
will always be like this. Otherwise, conservation of energy is not respected, right? You would get energy out of nowhere. You would get electricity like for nothing. Yeah, Marav.
Is there a cause-effect relationship here? Like the current changes, therefore the magnetic field changes?
Yeah, there is. It's a little bit like subtle here, but there is. Yeah, I'm not going to get into this. I will get into special relativity and so on and so on. Yeah. All right. So good. Okay. So now what you understand here, we're going to sort of come back to this here. Whoop, not that. This. This I can. Let me sort of drop it. Okay. So we're going to look at this here. That's not what I want. So we're going to look at this, and we're going to sort of be able to predict, based on this second interpretation of Lenz's law, we're going to sort of be able to predict the direction of the direction of the current in the secondary coil, and also, and so on and so on. Okay, so let's do this here. All right, so I'm going to have, so let me put this a little bit. So let's have a transformer. And then, yeah. There you go. All right. So let's have a transformer here, and this is going to be the current. All right. So this is the primary side right here. All right. And let's have the current going this way. So that's the primary side. And let's have the current increasing. All right. So primary current increases. So let's have on this side here, we're going to have the other. So I'll put it in. Let's put it in red. So that's going to be. There you go. So that's the secondary side. Now, what you have to do here is you have to predict in which direction will the current be going, right, in the loop here. As the current in the primary coil is going this way, it is increasing. You remember, in order to get like a transformer to work, you must send a current that changes with time. Okay, in which direction will the secondary current, the induced current, be going? All right. Well, this is how you do this here. Let's figure out, first of all, let's figure out the magnetic field produced by the primary. Okay, so right here. So we're going to use right-hand rule number 2. So right-hand rule number 2, you wrap it in the direction of the conventional current. Your thumb is pointing down. So, whoops. So this is north and this is south. right? Now, this will set up a magnetic field. So the magnetic field will go like this, from north to south. And remember, magnetic field are always continuous, right? So this is the magnetic field here, right? BP. I'm showing only one. I'm not going to show them all, but showing only one. Now, if we look at this point right here, let's look at this point right here. The magnetic field here is going this way, right? And let's call here like BI here, right? All right, it's going up. In the second recoil, the magnetic field produced by the first one, right, is going inside the loop is going up. Now, what we're doing here is that we are increasing the current on this side. If we are increasing the current, then the magnitude of the magnetic field become greater. So what will happen here is this. So what will happen is that the magnetic field right here will increase, right? Will increase, let's say it increases to this, right? Well, the change in magnetic field produced by the first will be like this. So there's been an increase in magnetic field intensity inside the second recoil. Well, as a matter of fact, everywhere, but here, inside the second recoil. Now, the second way of looking at Lenz law tells you this. This coil will react in such a way as to create a magnetic field that will sort of offset what has happened here. It has increased. So in order to make sure that the magnetic field inside goes back to what it was before, it has to output a magnetic field that goes down, right? So it has to output a magnetic field that goes down. Right? It has to, because it has to oppose the change here in magnetic field that has occurred right here. Well, magnetic field are never they never end, never start, right? So it goes all around. All right. Okay, so this is the induced. This is the magnetic field from the second recoil. Well, you remember that outside a coil, it goes from north to south. So that means that this is north, and this means that this is south. Right? Well, then you use right-hand rule number 2. So if this is north, if north is right here, so the current in the second recoil is going to go this way. And there we go. Whoops. So the current in the coil will be going that way. All right. So as the current, so once again, as the current goes in this direction in this primary coil and the current increases, the secondary current in the other coil will go like this. Okay, go like that. Is that okay? So this is a way to sort of predict in which direction the current will go in the secondary coil. Yeah, Jason?
This is only the case if the current increases and not when the
No,
current
it depends on the direction of the current, right? If the current in the primary coil increases but the current is going in the other direction. All right, if the current is going in the other direction, right? So I'm gonna do this something here, but I want to erase it like very soon. It's going this way instead. Now so the north will be up, right? And the south will be here. So what will happen here is the magnetic field produced by the primary coil will go, instead of going like this, will go like that, right? And now
Yeah.
the magnetic field will be pointing down. If it is pointing down and then the current increases, then the magnetic field is becoming like stronger down. So there's a change towards the down. So this one here will react in such a way as to offset this increase in magnetic field going down. So you'll have to induce a magnetic field that is going up. And so this one here will be going up. And then, so if it goes up here, if it goes this way, so this is north now, and then the current in the coil the secondary coil will change. Is that okay?
Yeah.
Yeah. Marav?
When you assign the direction of the poles based on the direction of the magnetic field, do you assume that the inside of the transformer is like the inside of a magnet, so that you can say that south is at the top and north is at the bottom?
It's like an electromagnet. That's electromagnet just like has the same magnetic field as a bar magnet, right? So as I said here earlier, in a bar magnet, of course, you have the north and the south pole, and magnetic field always goes outside a magnet, a bar magnet, from north to south, and from inside south to north. Same thing happens with an electromagnet. So outside the electromagnet, you have one side is north, one side is south, and the magnetic field produced by this electromagnet goes from north to south outside the electromagnet and south to north inside the magnet, inside the electromagnet. Okay. All right. This core here, like this iron core here, is just to make the effect like more efficient. That's all. Okay. What I've shown here, you can take the iron core completely out, and it'll be the same phenomenon here. It just so happens you're not going to get like such a good like output of current here. What happens here, so when you put like the soft iron core here, is that you cause those magnetic lines to become constrained, to become closer together, and they come together, the magnetic field intensity is greater. So as the magnetic field intensity is greater, and blah blah blah, so on and so on. Okay. Although what I said, there's a loophole here, and if you pay close attention to what I said earlier, you should say that the strength of magnetic field doesn't really matter. It's the rate at which magnetic field changes with time that matters, right? But anyway, you good? Okay, so now when you look at this here, right? So when you look at these things here, you can sort of understand now is which direction the secondary current goes, right? So this one here, it's very, very hard to see here, but if I make this like a bit bigger here. So this location here, like the current is going, the primary coil is going like that. It's increasing, so the secondary coil here will have like the current going like this. At this point, the current is going in the same direction as the primary coil, but now it's decreasing. And this is decreasing, of course, it flips. So these circles here are the magnetic field produced by the secondary and the primary coil, right? So as the current here in the primary coil is going in the same direction, but now it's decreasing. So in the secondary coil, the current will go in the other direction, and so on and so on. Okay. All right. Okay. All right, so now like the last topic here is this, large scale electrical generation here. Okay, so generating electricity. Well, you know how to generate electricity now. So what you need is you need two coils. Well, What you need is you can use electromagnetic induction, right? And that was the purpose of the reply to this Dane who asked, like, Michael Faraday, what's the use of all of this? So Michael Faraday replied, what's the use of a newborn baby? All right, so it's not so much potential here, right? So you can create electricity by electromagnetic induction. So if I have a wire here and I want to set like wire set the current in the wire, what I need, I just have to have a little magnet that moves. That's it, and I'm creating electricity. Wow. Or I can do the other way around. I can have a magnet fixed and then have the coil like moving. In the same way, electromagnetic induction will kick in and I'll have an induced current. Well, this is the basis for electrical generation here, right? So basically, you have right here, you have what is called a generator. And the generator here, I know it's a very bad copy here, but you can see here, you have like a cylinder with wires on it. It's a coil. And then around the generator, what you have huge magnet, super huge magnet. And if you make this coil turn, then the coil will sort of see a very magnetic field, and then there'll be an induced current. So this is how electricity is being generated at the electrical plant. So the goal is to make this coil turn. Well, how do you make it turn? Well, you can see here, there's a shaft here. And the shaft here is connected to some blades right here. And this is called a turbine. And the role of turbine is just to rotate the shaft in such a way as to rotate the coil and then induce like electricity. Okay, so there are various ways you can sort of make those blades turn. One of the most common one is to release steam onto the blades, and then like so the steam will impact on the blades and then like cause the blades to turn, causing the shaft to turn, and then you have electrical energy being produced. All right. Okay, so there's three. We're going to look at three major like way of generating electricity, and the first one is fossil fuel. Fossil fuel is coal. You burn coal, oil, natural gas. You burn it. So what it means is you make it react with oxygen. You kickstart the reaction, and there's enormous amount of heat that is being generated. Right. So think of Titanic, right, or think of steamboats, right? So or the steam train, right, locomotive. So what they did in the past, they used the coal and they burned the coal, right, and it produces a lot of steam. So what they do with the steam? Well, they make it like go through like steam lines here, pipes, and then they make it like come out at the turbines, at the blades, so forcing the turbine to turn, or forcing the wheel of a locomotive to turn, forcing the wheel of the propeller of a steamboat engine to rotate, right? Propeller to rotate. All right, so this is called a boiler. And in very old houses, you still have boilers. Case in point, St. Robert. St. Robert, there's a boiler room. Okay, there's another way of creating thermal energy. So here, there's water here. So the boiler is to take the boiler is just to boil the water. So you have water here, and then the thermal energy released by the burning coal, oil, and natural gas will go into liquid water, and then we'll sort of turn this into vapor. Another way of boiling the water is to use a nuclear plant. So nuclear plant use nuclear fission. They break like little atoms, well, uranium atoms. And as they break those uranium atoms, it releases a lot of energy. And this energy, thermal energy, is used to boil water. So that's the same principle here. The other major type of large-scale electricity generation is the dam, hydroelectric plant. So hydroelectric plant, what they do is they keep water from falling a certain height. So they keep it. So that's the purpose of a dam. Dam is to sort of keep the water from flowing down. And what you're doing here is you're storing a lot of gravitational potential energy. Now you open this and then you let the water flow down. So the water will flow down, will lose gravitational potential energy, and will pick up kinetic energy. And at the bottom, what you do is you make this water hit like the blades of the turbines. So the turbine will rotate, and then the shaft will rotate, and the shaft here, so the coil here will rotate amongst stationary magnets, and you'll have like electrical energy being induced. Now, once the electrical energy is being induced, electrical current is being induced, it needs to be brought to your home. There we go, through high voltage lines. Yeah, so do I have, there we go. So this is the hydro generator or the fossil fuel generator or the nuclear generator here. So as a whole, it outputs a voltage, an induced voltage of about 18 to 24 kilovolts. Now, before like this current leaves the generator, it needs to be stepped up. The voltage needs to be stepped up, and you're going to sort of see why it needs to be stepped up. So here is my first generator. So step up transformer, it will sort of step up like the voltage from about 20 to 500 kilovolt. And now this is going to be carried over high voltage lines. So that's why it's called high voltage lines. Now, when it gets like to a major center, you certainly don't want to have 500 kilovolt coming into your house. Everything will explode. So there must be a way to bring it down. Of course, you can bring it down with step down transformer. You see like how useful transformers are. They can sort of transform voltage. And remember, you can only transform voltage if you have a current that varies with time. So only AC will work, not DC. All right, so when you get close, so there's a first major station here that will sort of take the 500 kilovolt down to about half of it, 230. When it gets even like closer, so there's another municipal station. We'll take it for 230 up to about like 27, 28. Okay, when it gets like even closer and closer, so there's transformer that will sort of take it from 28 to about like 4 kilovolts. And then finally, close to your home, you have a transformer. It may be, since you live mostly in York region, it's a new region here, so probably you've seen those boxes like perhaps gray or green, okay, kind of big, right? That's a transformer. So what it does, it takes the voltage at 4 and step it down to 240, and this is what is delivered to your home. You got 240 volts get to your home. Now, in your home, you have a distribution panel that will sort of split this into two, 120 volt. And so all outlets in the house will function across 120 volt, except for two, as we mentioned before. One is the stove that uses 240 volts. The other one is the dryer that also uses 240 volts. You may have also air conditioner device that also works under 240 volts. Okay, everything else is 120 volts. And of course, some factories needs like more voltage, so they may have like their own little substation here, step down transformer to do this. All right. Okay. All right. So why do they need to step it up? Well, the reason why they need to step it up is when you step up the voltage, when you carry current on very high voltage lines, you minimize the thermal energy loss, right? The current travels over long distances. So there's a lot of this energy, electrical energy, that is being lost as thermal energy. So by the time you get home, right, if for instance here, like the generator did not step it up, right? By the time you get to home, like you would get like almost like no voltage. All right, so that's why you need to step it up. Okay. Is there a chat here? Or someone like number 3? Let me see here. Yeah. Okay. Yeah. So the reason why it's a high voltage, once again, is to make sure that you minimize the thermal energy loss. So you're going to make use of two formula. So the rate at which electrical energy is lost in a current is given by this, right? So P is equal to VI. And the drop of electrical potential across a wire, you remember, is given by Ohm's law. So it's going to be this. R is, in this case, is the resistance of your transmission lines. Now, if you take 2 and put into 1, you get this. So this is the power loss in transmission lines. Okay. So this power loss, how much power is lost to thermal energy. Okay. Now, okay, so we'll do an example. Where this equation comes from is this. I'm going to sort of show you here in a second if you're so inclined. What you want here is this. You have the power from the generator, right? And so this is the power in here, right? In must be equal to power out by conservation of energy. Now, this power here, it goes into two things. It goes into thermal loss, so power lost. All right, as thermal energy, as heat, it's thermal energy, plus the power that the town needs. Yeah, I'm having a bit of issue here. Okay, let me make this. Oh, I can make it. There we go. So plus the power that the town needs. All right. Now, if you take this equation here, I'm going to put it like right here. The power generator will be this. So it will be like the generator, right? Generator times the current will be equal to the power loss as heat, which is like this, plus the power that the town needs. Okay. All right. So I'm going up here. I should have gone down here. Like I'm going really up this way. I'm going like down here. Oops. Okay, so you have to read this up. All right, so if you have a generator here, right, of certain generators, it leaves the step-up transformer with a certain voltage here, you know resistance, you know how much the town needs, then this is nothing else but a quadratic equation in Y, okay? It's just an equation. Instead of being Y, you can think of it as X, yes. Yes,
So,
Max.
okay.
All right.
So for generators, the power must be like really, really high, right?
Yeah, we'll do an example here in a second. Okay. All right. So so if you know like how much the power the town needs, the R, and you know this, you can solve for the roots, and you're gonna find like two solutions for a root. One will not make any sense, and one will make physical sense, and that's the one that you need to use. Okay. So this is where like this those formulas are coming from. Anyway, so let's do an example here. I'm going to go like a little. Okay, so electrical energy is generated at a voltage of 20 kilovolts and is supplied to a town which requires 1 megawatt of power. The transmission lines along which electrical energy flows has a resistance of 0.5 ohm. How will the power losses due to heating, so this one here, compare if the energy is transmitted at 500 kilovolt instead of 20 kilovolt, all right? So here, as I said, it leaves the generator as about 20 kilovolt. If did not step it up, right, how much would the power loss be? And if they do step up to 500 kilovolt, how much would it compare? All right, so this is what we're going to do. All right, so let's do this here. So let's put what we know. what do we know? We know like the very first voltage. So the very first voltage is, let me put this in. Okay, so the very first voltage is 20 kilovolts. The power that the town needs is 1 megawatt. The transmission line is this one here. Sorry, the resistance, 0.5 ohm. V2 is 500 kilovolts. And what we want to find, so this is called the power loss. Okay, so whatever, usually I call this like PL. Okay, so for the power loss, so that's L here. And so what do we want? We want the power loss in the first case, right? And compare this to the power loss in the second case, right? All right. And here's the thing that you have to be very careful about. You need, in order to find the power loss, you need to find the current that is being transported. And this is where like you guys make mistakes sometimes. Since you have the resistance and you have the voltage, you might think, okay, I'm going to use Ohm's law, right? I'm going to V is equal to IR, and I'm going to find the current. No, do not do this. In order to find the current here, you have to use this one right here. Okay, not this, not V equal IR. Okay. So, so the power. So let's look at. So let's find out I1. What is I1 equal to? What is that? All right. So I1. So it'll be, whoops, the power. All right. So the power will be this. So it's the power that the town needs. Equal to V1 times I1. If you isolate for I1, you get this over V1. So you have like 1 megawatt. So megawatt is 10 to the 6 watt over the voltage in the first case, which is like 20 times 10 to the 3 volts. So it'll give you like what, thousands, so 100 divided by, is it 50? Is it 50 amps, guys? Is that good? Is it 50? 1,000, yes or no? 50? Is it 50 amps? I don't get any answer here. Are you there?
Yeah.
Yeah.
Yeah, it's 50? Okay, good. All right, now we can sort of find the power loss. So the power loss will be equal to this. So I1 squared times R. So it'll be like 50 amps squared times 0.5 ohm. So that will give you, what is that? Like, so this is 50 square, which is like 2500 divided by 2. So it's this. All right. So the power loss due to in transmission line due to conversion in thermal energy is 1250 watts. So if the output, if they don't step it up, and the current, when the current leaves the station, the voltage is 20 kilovolt, you have like 1250 watts of this 1,000, like you want 1,000,000, right? You might say, well, that's not bad. It's, it's not that bad. It's about what, 0.1%, 1% loss compared to what you need. That's okay. But still like a lot. Now, what I'm gonna ask you here, like, is you're gonna do the same thing for V2. So you're gonna sort of figure out how much is the current when the generating station is outputting at 500 kilovolt instead of 20. Well, if we do this like very quickly here, it'll be like 1,000,000 divided by 500 times. So it's what's that done. So I think it's going to give you, well, let's do this like very quickly here. I said like you should do it, and I'm doing it. So down divided by V2. So it'll be 1 times 10 to the 6 watt divided by, so 5 times 10 to the 5 volts. And that will give you, what is that? Here's 0.5. Is it 2 amps?
Yeah.
2 amps? Yeah, 2 amps. All right, and then if you find the power loss times R, you get this. Two watt. Is that it? 2 watt. By pumping it, by making sure that you step up the voltage, right? You get only 2 watts that is lost. This is super small compared to how much the town needs. So this is the reason why they had to step it up. This is the reason why you have like high voltage lines. Okay, just to make sure that you have to minimize the voltage. Sorry, to minimize the power loss in transmission lines. Okay, and as I said, like to find the current, you use this formula: P is equal to VI, not Ohm's law. Okay, do not use Ohm's law.
Wait, sir, why can't we use Ohm's law?
Well, I'm not going to tell you. Don't use Ohm's law. It's okay. It has to do like here, and just don't use it. All right. Are you good? All right. So the very last part. So we're going to sort of look at application of electromagnets. So now there's like 3 questions you have to do, and that's it. That has to do with this stuff here, right? So you'll be done in no time. Okay. So it'll be done. Okay. So let's look at some application of electromagnets. Let's look at a old-fashioned electric bell. So in old-fashioned electric bells, you may have noticed here like the gong, and you have a little hammer. And what you want is you want a hammer to repeatedly hit like the gong, right? So how is this done? Well, what you have here is you have the hammer, and this is all metal. This one here, it's also metal, but it's flexible. It's not like super flexible, but it's a little flexible. Okay, so if you push it, it comes back. There's a restoring force, right? Hooke's law, restoring force. Okay. All right. So let's say there's a fire here, and what you do is you set the alarm on. When you pull something, what you do is you actually close the circuit, right? So you're closing the circuit. So you're closing this circuit here. So when you set this, close the circuit. So what will happen here is that, so this is your battery right here. So there'll be current flowing through it. And now there's an electromagnet right here, right? So what happens here is that this will serve as magnets, electromagnets. So here, if you find the direction here, you can see here that this is south, this is south. It doesn't really matter here. The key point here is that this is made of, I should have said, this is not only made of metal, this is made of iron. So what happens here is that these turns into magnets. So it will sort of attract this hammer towards the gong, right?
Wait, sir.
Yeah.
For the bottom one, shouldn't the current be going the other way?
Perhaps, yeah. I don't know. Yeah, you're right. Okay.
Okay.
Yeah, all right. That's why I didn't want to do it here, because I want to get into, all right, so it goes behind, goes, yeah. Okay, and then definitely. Okay, the key point here is that it's going to behave as magnets, all right, and I will sort of attract this. So it hits the gong, but what you want is you want this hammer to hit it again. So what happens here is this: it hits the gong, the hammer, but here it loses contact. So as it loses contact, the current stops. If the current stops, then there's no electromagnet. No electromagnet, now it's not attracted towards the gong anymore. And since it's like hardly flexible, it'll come back to its original position, and then it will make contact again, and then you'll have current, and the whole thing repeats itself. So that's what makes this repetitive sound here. All right. And the only way to stop this is, of course, to open the circuit. Is that okay? So that's how an electrical bell works. Okay, a solenoid switch. Sometimes you want to cause something to happen without being close to it. Let's say, I don't know, you want to drop like a vial of COVID-19. Well, COVID-19 is the disease. Let's say you want to drop like a test tube of, what's it called? SARS-CoV-2, something like that. That's the virus causing COVID-19, right? But you don't want to get close to it, right? So you want a little machine here like to turn this, but you don't want to be close. All right, so how can you do this? Well, you can do this with what is called a solenoid switch. Here's the iron core right here. This is your coil right there. And you want the iron core, you want the iron core to move. And as it moves, it causes something else to happen. All right, so it causes like a switch to fall back, or it causes something to happen, right? And of course, like, so in order to move the core, what you can do, it's made of iron here, what you can do is you can have like your little coil here, and you have your wires around this, and then you are very far away. So here, like those wires here extend very, very far away, right? And then you have your switch very far away, so you're not close to it. And what you do here is, of course, you close it. Well, as you close it, there'll be a current being set up. All right. So this will work as a electromagnet, and it will sort of pull the iron core in. And as it pulls the iron core in, you remember, you're very far. The switch is very far. So you pull the iron core is being pulled, and then cause something to happen. I know, cause the test tube to fall or whatever. Okay, so this is called a solenoid switch. It's very practical when you don't want to be close to something that you want to change, right? This is called an actuator, something you want to cause something to happen without being close to it. If you notice, sometimes in cars, when you turn the ignition key, and you may sort of hit, sometimes like if it doesn't work, you may hear like click, click, click. Well, this is exactly what you're doing here. This is a solenoid switch, and the click you're hearing is something that you're causing it to move, all right? To move. So this is called a solenoid switch. Or a relay. Sometimes it's called a relay. Okay, last one I'm going to talk about, wow, almost there, is a loudspeaker, a conventional loudspeaker. There's different loudspeakers. Most loudspeakers like work under this principle here. if you've ever like used lifted a true loudspeaker here, you know it's a little heavy, and it's heavy because there's a huge permanent magnet here, and it is on this shape here. So here, this is a south pole, the magnet, and here you have the cylinder that pops out. Here is the north pole. Now, what you have around this cylinder here is another cylinder that is held in place in such a way that it doesn't touch the magnetic north pole here, right? Magnetic material. It's held in place with like some flexible structure. It's called a spider, actually. All right. But this cone here, right, which is like in cheap speakers, is made up of probably a cardboard, is free to move like back and forth, right? And then around this cardboard, or if you have more expensive one, like it would be Kevlar or some sort, you have like wires being wound around the cardboard cylinder. It's glued on. All right. And then at the end of this cardboard cylinder here, you have a cone. So once again, cheap speaker, cardboard, more expensive speakers, probably Kevlar, something like very firm. Okay. Okay. So what you want here, the speakers, you want it to create a sound waves. How do you create a sound? You remember sound waves is longitudinal waves. It's made up of compression. The air molecules are very compressed together, and rarefaction, where the molecules are farther apart. All right. Or a series of high pressure and low pressure. So how do you create this? Well, you create this with a little cone. So you move the cone forward and you compress like a lot of air particles, and this compression like spreads throughout the room, gets into your ears, and then forces your membrane, your ears, to vibrate with the same frequency as that of the speaker, and then you perceive this to be a certain sound, certain pitch. All right, so let's say here you want to produce a thousand hertz sound waves. So what you want here, you want this cone to go back and forth like 1,000 times, 1,000 cycles a second. All right, so how is this achieved? Well, if you want to produce a 1,000 hertz sound wave, your amplifier has to output a current or a voltage that changes at a frequency of 1,000 hertz. Okay, so here, this is the wire here. This is connected to the cardboard cylinder of this whole thing here, and of course those cables are connected to amplifiers. All right. So at this point here, this wire here is connected to the higher electrical potential side of the amplifier, and this one is connected to the lower electrical potential side of the wire. So here what we have a front, right? This is the front. All right. So if I follow the current goes like this. All right. So that's the current right here. Current go like that around the wires. Now this is north and this is south. You remember that outside of magnet it goes from north to south. And actually, in this case here, the magnetic field are going like this, radially out. All right, so they're going outwards. Okay, going outwards. Wow, it's very hard to see. Let me sort of put it in. Perhaps that's better. All right. There you go. It's a little bit better, but not really. I don't know. What am I going to use here? What would be good contrast? There we go. Perhaps orange. I apologize, guys. I wanted to see contrast is so bad. Okay, so let's see here. Is it going to be better? Yeah. Oh, look at that. That's beautiful. There we go. That's better. All right. Okay. So now we're going to sort of look at this region here, this region of the current here, the coil. At this region here, the coil, the current is going this way, right? FBI. The magnetic field is going that way. So the force on this little portion here is going inwards. And you can convince yourself that all around this coil here, the force will be inwards. Well, the coil will go inwards, the magnetic force going inwards. Now, this coil is connected, is glued to this cone here. So what will happen here is the cone will move backwards. But what you want is you want like the cone also to move forward. So what happens here, if you send a signal, the amplifier sends a 100,000 hertz signal. So what happens here is that half a cycle later, this wire here will be connected to the negative side, and this one will be connected to the positive side. And the effect of which will sort of make the current in the wire going in a different direction. The magnetic field is going in the same direction as before. So the force now on the wire will be in the other direction. So now the cone will go forward and back and forth. So if you send a 1,000 hertz signal, electrical signal to the speaker, the cone will go back and forth at a frequency of 1,000 hertz, creating therefore 1,000 hertz sound waves. And then you're gonna hear the pitch of a 1,000 hertz sound waves. So this is an application of motor principles, and this is how a classical loudspeaker works. Okay, there's different. There's a what we call electrostatic speakers, but most speakers like work under this this model here. Okay, questions? Okay. Well, that's it, guys. So do the homework. There's only 3 questions. Tomorrow I have a meeting from 9 to 10. So so the help session, if you need a help session, although the last 2 I was like pretty lonely. Nobody make use of the help session. Anyway, so if you need help, like I'll be on like from 10 to 11 tomorrow, not 9:45 to 10:45. Okay. So next week, Monday, you will have no class. There's something else to do on that day with my grade 9. So there won't be any class on Monday, and we'll meet on Tuesday at 10:30. And then what I'll do is I'll talk a little bit about the sound unit, like something that you may not, I'll talk a little bit about Doppler effect and also a bit more about musical instrument and different types of harmonics and all the like. Yeah, so I'll take this like probably 2 days. So Monday, Tuesday and Wednesday. And then Thursday, you'll have to submit your ISU, sound ISU. Now, so make sure that you check my website because I will put like I will post some handouts that you need to download and print for the sound. Whatever I send you as a handout, please do not put this as part of your package. Okay, you can put it, it can be part of your notes, but it should be separate. I don't want to see this in your sound ISU package. All right, so make sure you don't put them there.
Wait, do you want a picture of our notes as well?
Was that?
Do you want our notes as well, or just the questions?
No, notes and questions.
Okay.
Yeah. So I will explain a little bit more like next week on Tuesday. So what I want for the ISU, I want you to take a picture each page, to turn this into a PDF file, and I want you to assemble all those PDF files into one big one. And so I will sort of give you like a free software that you can do that. You can combine PDF file. You may have it but you have to pay, right? Like Acrobat Pro will do it, but if you don't have Acrobat Pro, then you need to have another software that you don't have to pay for. So I know a software that does this. So combine all the PDF files and then you submit this in order. All right, guys. So that's it. So it was like a little long, but we're done. So done for electromagnetism unit. Okay. So I'll see you on Tuesday. On Tuesday at 10:30. All right. So once again, no class on Monday. So check the website also for those additional handouts. Okay. All right. Okay. So until then, have a great weekend. I think it's going to be terrific. So go out, go on bicycles, or do some exercise, take a bit of fresh air, but stay safe. And I'll see you on Tuesday. All right. Okay. Bye.